Okay, Jackson, you can thank Bella for reminding me to record this. Okay, let's put that down there. All right, so let's come back to this. So if we had an expression like this, it's not quite as clear what this angle theta might be and what's happening to the angle theta. Is it being stretched? Is it being compressed? Is it being shifted? We don't know. The other thing is, look at these coefficients. 4 and 4 square roots of 3, it's not even in the range. This is sine. It's not even in the range. 4 square root of 3 of sine isn't even in the range of sine. So we've got to have some method of being able to take this and work with the information given so we can create a single sine function. Could be cosine as well, but we're going to stick with sines for today. So the first question that should come to your mind is it even reasonable to assume we could take something like this that has a sine and a cosine function in it and think that we can find a function for a sinusoidal, a single sinusoidal function. So if you put this into your calculator or GeoGebra or Demos, this is the graph that you see. And clearly you look at that graph and you say, hey, yeah, maybe my amplitude is stretched and maybe it's compressed, but I definitely can see this as a sinusoidal function. So it is going to be possible, even though this looks very complicated, to represent this thing in this form right here. We're going to be able to put this into the following form. A times sine of bx plus c. We're going to be able to take this whole thing and write it as a single sine function. So a lot of these numbers should look very familiar to you. At one point you had a plus d out there for your midline, right? But we're used to this. This number has to do with our period. If we know our period, we can find this number because 2 pi divided by the period gives us b. This is just our amplitude, right? And c is a phase shift or a horizontal shift of our function. So the good news is we know one of these values right now. Just from looking at this, we know one of those numbers. Can anybody, it's like we can play I Spy here. Can anybody find one of those, A, B, or C, from looking at that function right there, that expression? What? B equals 2. Notice the only reason we can do this is both of these functions have the same period. 2 pi divided by 2 is pi. 2 pi divided by 2 is pi. So in your book, they call this combining waves with equal periods. If this wasn't 2x and 2x, we couldn't use this particular method. So right now, the 2 is sitting in the spot where b is. So I can already fill in one of these 3 unknown values by just putting the 2 in there. So my job, your job, is going to be to find the values of A and C. So that's what we're about to do now. All right. So here's what I just wrote here. Both sine and cosine have the same horizontal compression. This is being compressed horizontally, and this is being compressed the same factor of 1/2. Divide all your x values by 2, or 2 complete cycles of sine and cosine in the period of from 0 to 2 pi. So they're both the same period. They have different stretches going on vertically. So let's see, what we want to do now is let's see if we can take this expression and make it look like this. We're going to have some coefficient times sine of bx, another coefficient times cosine of bx. And eventually our job is to turn it into this equivalent equation here. So let's take a look from our example right here. What is the value of m and what is the value of n? So what's our value of m in this particular case? 4 square roots of 3, right? Because m is the coefficient of our sine bx. So that's 4 square roots of 3. And n is equal to -4. Okay, so that's what I know so far. All right, now we can turn the page. So we know, and we can throw b in there as well. B is 2. We know that much so far. All right. Okay, so to derive, to go from here to here is going to stretch your math muscles. Embrace the struggle. It's not too bad. It's going to be long, but in the end, you'll come up with a generic way of going from any expression that looks like we just did 4 square root of 3 sine 2x minus 4 cosine 2x into a single function. And I've talked to Ian Winokur, who teaches calculus for us, about why do we do these kinds of things. And he says it's really important in pre-calculus to start increasing. He called it a sweet spot. I said, I don't think the students are going to feel like it's a sweet spot today, but start to increase the level of seeing proofs and derivations that just take you a little step beyond where you've been. So when you get to calculus, you start getting used to seeing these types of things. So what we're going to do is we're going to start with the right side, and we're going to expand this using our sign addition function, addition identity for sign. So we're just going to do what we did earlier. So a, and now it's going to be times some big thing. We're just going to expand sine of bx plus c. So let's do that. Someone want to help me with that? Sine of bx plus c? Solomon, can you help me with that? Can you expand this for us? Okay. Anybody? Bella? Yep. Good. All right. Sine of c times cosine of bx. All right. Well, all we got to do now is distribute the a to each term. So I'm just going to remove those brackets and put an a in front of each one of these, like this. And I'm going to change my color now when I go in here. I'll keep the a blue, and it's sine c times cosine bx. I'll keep a as purple here. Okay, so there we go. We're trying to show that this right side is equal to this left side. So let's throw the left side in now, right at this point. So let's put the left side in. We've got m sine of bx plus n cosine of bx. So we got an addition problem on the left side, an addition problem on the right side. So this term of the right side, that part of the addition problem, goes with this one. And this term goes with this one. One's a sine and one's a cosine of bx. All right, so what we want to do is we want to set the red circles equal to each other and the purple circles equal to each other. So m sine of bx, that's my red circle, is going to equal my other red circle. I'm setting those two things equal. We've got to make them equal, so we're going to do our best here. Then I'm going to set the two purple circles equal to each other. Okay. Why are we doing this? Because what do we need to do? We need to figure out how to determine capital A, the value for capital A, and the value for capital C. So here's two equations that have A in them. So we can solve for A. So what would we do to solve for A here? What would we divide both sides by? What's the coefficient of A here? Remember I said it can be a factor or any group of factors. What's multiplying A? Yeah, times cosine C, right? So can you see right now that if I divide both sides by sine of bx, the sine of bx disappears to 1? Can we just kind of knock that out of the equation right now? Okay, so we're just going to knock that out right now. All right, so we get m equals A times the cosine of some value C. So to solve for A, it's this coefficient up here, m, divided by the cosine of C. So we got two variations here. We've got an equation solved for m, which is probably going to come in handy because we're going to need to figure out what m is. And we've got an equation solved for a, which is going to come in handy because we need to figure out what a is. So we're going to use both of these equations. Similarly, on the right-hand side, what can we get rid of in that equation? Yeah, cosine bx. If you divide both sides by cosine bx, you'll get 1. So you have n equals A times the sine of C. So that's one equation. That solves for n, which we're going to need. And then to solve for sine of C, we divide both sides by A. Once we know A and we know n, then we're going to be able to find C. All right. So this next part is where you wouldn't think about doing this. And so how do you explain this? When you have to do proofs in mathematics, you learn lots of strategies. So clearly the first people that worked this out use this strategy, probably after trying many of them. It wouldn't come to you like, it's not intuitive that it's going to come to you right now. But what we do now is we're going to square m and n and add them together. So we're going to do this. We're going to say, what does m squared plus n squared look like? And you'll see in a minute, if you just hold on, why we're doing this. So if we square m, we're going to square this whole thing here. So the a gets squared and the cosine of c gets squared. That's m squared. You just square each factor. That's just your exponent properties. Like 2x squared is 4x squared. Then we're going to square n, and it's going to look like this. A squared times sine square c. Hopefully you start to see something that might look a little familiar in there. Is anybody seeing anything that maybe would help us get to A eventually? Double angle identity. Almost. The double angle identity is cosine squared minus sine squared, but you're on the right track. Think about how you got that double angle identity. Huh? What's sine squared plus cosine squared equal? 1, right? You got to have that imprinted on your forehead, right? Maybe that should be the tattoo I finally get right up and down my arm. Okay. Then they'll know I'm really a nerd, right? But how do I get cosine squared plus sine squared here? What do I got to do first? I'm trying to solve for a. Factor out a squared. So let's factor out the a squared. And oh my goodness, is this just beautiful inside here. All that stuff just becomes 1. Woo-hoo! That makes life so easy. Because now we have this relationship between the coefficients of our original problem. M squared plus n squared is a squared. So let's go back to that problem. What was it? It was 4 square roots of 3 times sine of 2x. We're getting there. Minus 4 cosine of 2x. We're now ready to find, and we want to put it into this form. We're like almost home. Because we saw that b was 2. So we can put the 2 in there. Let's put the 2 in. B is 2. We can tell that without doing any work at all, just from looking at our original expression, they have to have the same period. So B is 2 from both of them, so we can erase that. Now we're ready to find A. We already identified that this is M and that this is N. So now that we know M and N, we can find A. So we square M, we square N, and that equals A squared. Remember, we're trying to solve for A, so we got a little more work to do once we get A squared. So if we square 4 and we square roots of 3, we get 16 times 3 plus 16 equals A squared. That's 48 plus 16 equals A squared. Yay, it's a beautiful, perfect square. A squared is 64. In this case, we're going to use A as the positive square root. That's where we always start, unless we're always dealing with the sign starting at the midline. So now you can erase that A, and voila, you are almost there. Look at that. Yeah, because you got this. There is a reason. And the reason is you had to come back to this Pythagorean theorem over here by squaring each individual term. So it's going to have that form of the Pythagorean theorem. Yeah. Notice I didn't say square the quantity M plus N because that would look very differently. All right. What's the last thing we have to determine? Right up here, we've got A, we've got B, now we've got to find C. So that's where you come back to these two equations right here. We now know A, we now know M, we can definitely find the cosine of C by using inverse functions, and the same thing here. So let's go back here. To find C, we're going to use this idea, M over the cosine of C equals A. So let's fill that all out. So M is what? 4 square roots of 3, that's right here. M is the coefficient of the sine, over cosine of C is equal to 8. So you can see if I multiply, this is just a proportion here. I want to solve for C, so I've got to get that out of the denominator. So you can also see if you can multiply both sides by cosine of C and then divide by 8. I'm not going to go through those steps unless you really need me to. I will. But this basically becomes this with 1 or 2 steps of algebra. And what does that reduce to? Square root of 3 over 2. Oh my goodness. I got a good feeling going on. I don't even have to use my calculator now. Yes. All right. We're going to get 2 possible answers here for C once we use the inverse function, but we're taking both the cosine of that function and the sine of that same function. So one of them are going to be eliminated. We'll have 2 possibilities, and then once we figure out what sine of C is, we know we can only be in one quadrant. So let's see. Cosine inverse of square root of 3 over 2 is equal to C. We take the cosine inverse of both sides. So C has 2 possibilities here. The cosine is positive in the first quadrant, so this could be pi over 6. Or C could be 11 pi over 6. It could also be in your fourth quadrant. Right now, we don't know which angle we're dealing with because we got those 2 possibilities. But C is definitely a unique angle, just one. So now let's play this same game with the sine of C. So N over the sine of C is equal to A. So sine of C equals N over A. N was what? -4. A was 8. So that reduces to -1/2. And you really don't need to go any further, folks, because Where is cosine positive and sine negative? Which quadrant? 1 or 4? 4. So that means C has to be 11 pi over 6. And we are now done. We have taken that fairly complicated thing, and with a derivation, now you'll never have to go through that derivation again. You just have to know this, so you can find A. You'll always see M and N. And you have to know these two right here. Now, some books, if some of you like to experiment with books and stuff, you can see if you took this and divided it by this, you would have a tangent function. And it would just be the tangent of M over N over M. But I don't want to do it that way. I think this way is just a little more easier to deal with. So those problems from 7, this is all 7-2 right here. This is 7-2, and this is one or two of the problems I asked you to skip when we were covering 7-2. It would have been way too much to do this all in one lesson. Okay. So now let's use this information to now solve equations. That's really where this is all going. This is really an important result. So we have this expression on the right. There's no way we can really, maybe if we start looking at sines of double angles and cosines of double angles, maybe we could get that left side into one trig function, but man, it just seems like it'd be a lot of work. But now we're going to be able to write this right now, so it looks like this: A sine of bx plus c, because we just figured out generically how to do it for every single possibility here. So we know m is 3. M is the coefficient of our sine of 2x. N is 4. And what's b again, Peter? 2. Right. B is sitting right there. That's the nice thing. So we get a sine of 2x plus c. So the only thing you'll ever have to determine in any problem you do like this is the value for a and the value for c. So let's figure out the value for a. All right, so a is m squared plus n squared equals a squared. M is 3. 3 squared plus 4 squared is a squared. 9 plus 16 is 25, so a is 5. Oh, thank goodness, it's a nice number. Won't always be, but hey, we'll take it. Okay, so now we still have to find c, and then we can start to solve our equation. Okay, so how are we going to find c? We go back right here. We use this right here. M divided by cosine of c equals a. So m is 3, divided by the sine of c equals a, which is 5. So I multiply both sides by sine of c and then divide both sides by 5, and I get 3/5 equals the sine of c. Okay, I also didn't fully read my instructions, which happens a lot. I do it too, as you do. They want the first 2 positive solutions only. Okay. Yep. Oh, it's supposed to be cosine. M over cosine. Sorry. Is that what you mean? Yep. Thank you. Cosine. Thank you. Okay, so we have to find what angle gives us the cosine of 3/5. That's not one of our nice ones. So we have to take the arc sine of both sides or the inverse cosine. So let's do that. Cosine inverse of 3/5 equals c. Oh, we got to pull out our calculators. We do know something, cosine is positive, right? Cosine's going to be positive. So we're either going to be in the first quadrant or our fourth quadrant. So let's find the angle that gives us a cosine value of 3/5. So we pull out our calculators and let's see what we get. All right, cosine inverse of 3/5. 3/5 is the same as 0.6. And we get roughly 0.9272 or 3, 0.927. I'll just go with 3 places. So C is roughly 0.927. Throw in the 3. All right. All right. So if we just wanted to, we don't have to be accurate when we remember C is some angle here. We know pi over 2 is what, about 1.57. So we're going to be a little closer to the top. So here's our angle, 0.9273. And so what's the corresponding angle down here going to be? It's going to be 2 pi. Yep, go ahead. Right, roughly, yeah. So the other angle is 2 pi minus 0.9273. So we throw that into our calculator. These will take a long time to solve. Just give yourself lots of time. 2 pi minus 0.9273. So we got 2 values. That's about, oh shoot, come on, stay up there. Did I use the other calculator? Yeah, 5.36, say. Okay, I've got 2 calculators going here. 5 point, did anybody hear me? Thank you. All right. All right, so which value for C are we going to use? Here's 2 possibilities for C. Well, that's where you have to go back and look at your sine of C. So sine of C is what? N over A is sine of C. So that's going to help us determine N was 4, A was 5. Oh, so sine of C is also positive. So that helps you to figure out, is it going to be this value or that value? So since sine is positive as well, we know it's going to be the angle in our first quadrant. So we're going to use the 0.9273. So we cross out this value and we go with this value for C. All right, now you have your left side of your equation. 5 sine of 2x plus 0.9273 is equal to 1. And this is lesson 28. This is why we did lesson 28. Lesson 28 taught us how to solve these equations. We'll just get started, and then I think you can do it on your own. Some of you like to use the U substitution. I haven't done that for a while. So let U equal all this stuff inside, 2x plus 0.9273. It makes it a lot easier on our eyes to see something like this. That looks a lot friendlier than all that other stuff. So we divide both sides by 1/5. Now we take the inverse sine of both sides, or the arc sine. Okay, now we've got to use our calculator to find the inverse sine of 0.2. So we pull out our calculators. Okay, clear inverse sine of 0.2 is 0.201. Okay, so 0.201 is equal to U. We also know there's another solution by symmetry. There's another positive solution. If we look at our unit circle, here's 0.201. We've got another reference angle over here in quadrant 2 where sine is also positive. So our other possibility is pi minus 0.201. You can either round that off or keep it like that. If you round it off, it's about 2.94. Okay, so here's 2 possibilities. And then what's our other possibility? Let's do like 3 possibilities because we got to come up with 2, and one of them might get crossed off because it might be negative. The other possibility is just to add 2 pi to this first one, right? Get the same terminal side, so that's another possibility for U. U equals 2 pi plus 0.201. And let's see. So I don't know what that is off the top of my head. Thank you. 6.484. All right. Now what do you do with all of this? These are your U values, but U is equal to this up here. So all you do is do your substitution back. You said U is equal to 2x plus 0.9273. So one of the possibilities for U is this number right here, 0.201. Oh, this is supposed to equal 1. Right? So what do we have for U here? 0.201. Right? So you can subtract that from 1. Okay, and you can proceed now. You all know how to do this. You've done it over and over again, okay, to solve that equation. This isn't really the gist of today's anyway. So I really want you, because there's only 12 minutes left, to start working on these, okay? Uh-oh, what happened to that? It looks like I lost that lecture. Sorry, folks. It closed out on me. Yeah, I don't know. I meant to, yeah, I'm still recording.